Hello, today we will talk about Monte Carlo ray tracing. Last time we talked about the rendering equation, but this is actually the rather complex integral equation. So basically, to compute this solution, we need to rely upon some sort of this numerical approach. I will talk about that one. So here today we will talk about the sampling approach for solving the rendering equation, which is nothing but a Monte Carlo integration. And then based on Monte Carlo integration, we will design this basic structure of the Monte Carlo based ray tracing. And then we'll talk about the Russian roulette for terminating the recursive structure of the Monte Carlo ray tracing. And then in the end, the final Monte Carlo ray tracing is nothing but this path tracing. So today we'll talk about this Monte Carlo integration, also Monte Carlo ray tracing, which is actually which require lots of actually the details, but we'll skip the details. Also, we'll also skip some sort of the theoretical analysis, which is very important. But in this class, we'll talk about only high-level idea. So if you want to know the detail, I recommend you to look into this chapter 14 and 15 of my book. As we mentioned before, the radiance evaluation is the fundamental problem for evaluating global illumination techniques. So basically at this point, suppose that we wanted to compute basically we have this ray from here to that direction. That we need to compute the radiance value that starts from x to that direction. In this case, theta, right? So basically, this is nothing but evaluate radiance at a given surface point in a given direction. Basically, unless we don't have any participating media along this ray, basically we can have this invariance. So in other words, this radiance does not vary from here to there. So once we know the radiance for a ray, then we can evaluate the ray. We can fully perform the ray tracing. The problem is that there are so many passes. Here, suppose that we want to compute the radiance value from here, from the point of x to that direction. Then we need to there could be the infinite number of these paths. I mean, this light source and the one basically there could be the incoming radiance from here to the x, or there could be one bounce from here hitting this surface and then hitting there. Also, there are another path from here, we intersecting here and there, or there could be this multiple bounce. The light source, the photon emitting from here, hitting there, and then ending up the X here. So there could be so many possible passes. So you probably remember that this is the radiance, this is the random equation in hemispherical formulation. Basically, I will mainly use the hemispherical formulation. So again, basically, to compute the reflected radiance from x to the direction of theta, we need to consider all the incoming radiance over this psi over the hemisphere. Basically, this is the incoming radiance, and then this is a BRDF. And then also we need to adjust the oblique surface, this cosine theta x over the solid angle. So again, there are so many passes. So basically we need to integrate all the incoming direction here over the hemisphere. And then basically analytically solving the DC random equation almost impossible. Obviously, in some very simple cases, there could be some of the simple analytical solution. But in general case, we don't have the we don't have any analytical solution. So as a result, we need to rely upon some sort of approximation over the numerical techniques. Only on as a numerical approach for solving this kind of complex integral equation, Monte Carlo integration arise. This is a numerical tool to evaluate integrals. So basically, the Monte Carlo integration is simply used the sampling technique. Since it used some sort of random sampling, it has this stochastic error. But basically this unbiased technique, which is very important concept for the rendering. Unbiased means on average we get the right answer. That's the main definition of the unbiased. since this is sampling technique, so on average means that once we have the infinite number of the samples, basically we can, on average, we can get a right answer. This one example, suppose that we need to evaluate a simple integral, one-dimensional integral. This is the function f of x defined in the domain from the a to b, and it has this kind of shape. And basically, we want to compute this. We want to evaluate this integral function, and we want to compute this I value. One simple approach that we talked about before, maybe in the high school, it's a deterministic integration, also known as the quadrature rules. You might remember that we actually discretize this function space with these simple shapes, and then we evaluate. We integrate this area of the subdomains, something like this. So as we had a very small, infinitely small size of this rectangular shape, on average we can get the right answer, right? But this approach is that this determinist approach. Obviously, basically it means that we need to have the infinite number of infinite number of subdomains, which takes a lot of time, right? Instead of that, we wanted to use some sort of the sampling approach. So now I'd like to talk about some of sampling approach. Basically, here I'll talk about primary estimator for Monte Carlo technique, which is nothing but just using the one random samples. Suppose that this is the integration function we want to compute, and primary estimate is nothing but just using we just generate a random number in the range of domain of this function. In this case, 0 to 1. We generate just a random number x bar, and then we just using the x bar this function as a primary estimator. Then basically, if we compute the average of this primary estimator, then we need to integrate. You might remember that you need to recall computing average of the random samples, and then we need to integrate this. We need to integrate this primary estimator. In this case, x bar. In this case, this x actually in the range of 0 to 1. Basically, here actually I used x bar, but we should use the x bar here. But I used the x again here. This is a kind of abuse of notation, and then basically we just use the function the variable x here, and then since this is actually random sample, we need to multiply this primary estimator with each probability. In this case, p of x. So here I used this random uniform sampling. So in this case, p of x is simply 1. Then in the end, this the average of this primary estimator is turn out to be like this, and in the end, it's exactly the same to this one here. This is the integration that we want to compute. In this case, a and b turn out to be the 0 to 1. Now let's talk about another example here. Basically, the same simple function, but in this case, domain of this function starts from the a to b, not 0 to 1. And in this case, we define the primary estimator, fx. Actually, I used x sub s, but but here, basically, in this case, the primary estimator defined by I will just simply use f of x divided by the p of x. So in this case, p of x actually turn out to be the p of x turn out to be the 1 over a minus b, which is then f of x and divided by p of x turn out to be fx multiplied by the b minus a here, and then average of this primary estimator turn out to be like this. So we integrate in the range of a to b fx, and then basically we put this primary estimator here, and then also we need to consider when to multiply with the p of x. And as I mentioned before, p of x defined basically p of x nothing but 1 over b minus a. Why? If we integrate basically if we integrate the p of x in this range, that should be the 1, right? If we integrate this value over the a to b, then it should be the 1, right? That's why the p of x is turned out to be 1 over ba. Then these two terms cancel each other. Then in the end, this is nothing but the original function, the original integral that we want to compute. So that's why we want to cancel the p of x here. That's why actually we define the primary estimator f of x divided by the p of x. Again, basically the on average, our the simple primary estimator for the Monte Carlo integration is also the unbiased estimator. Uh, Basically, so far we talked about average, but we need to think about what's the error of the Monte Carlo integration. Variant as an to measure the error of the Monte Carlo integration, we can simply use the variance of the estimator. This is nothing but a measure of the stochastic error. So in this case, the variance is nothing but basically we want to measure the difference between our estimator, f of x divided by the p of x. Basically, the difference between our estimator and the ground truth. In this case, I is the actual ground truth value of the integration function, and basically their distance. In other words, basically we measure their difference and we take the square, and then basically the variance also they're measured by that value multiplied by the p of x in the range of the a to b. Basically, this is the variance equation in the random samples. Basically, there could be there many ways of reducing this variance. As an example of reducing the variance, we will briefly talk about important sampling later on. Then we can simply then I will talk about the secondary estimator that also simply using the primary estimator multiple times. But this is actually typically basically this is the typical estimator that we are using for evaluating random equation. So instead of just using one sample, we just generate n different random samples, right? So basically, to evaluate this function, we using the n different random samples. Some cases, some random samples happen to be here, so that this at that case we just treat that this function of f of x has this area. Or we can also generate another random sample like this, then we actually treat that function has this kind of shapes. But there are n different samples, right? And then since there are n different samples, we need to take the average. In other words, we sum of those n different samples and we take the 1 of n, which is nothing but average. We can call this the actual secondary estimator. But basically, one can easily show that the variance of the secondary estimator, basically it's nothing but original distance variance of the prime estimator divided by n. In other words, as we had n different samples, the variance of variance of our estimator reducing down as a function of 1 of n, which is very important concept, which is very important property for the Monte Carlo estimator. Here, I'd like to show some of the example here. We want to evaluate this integration. This very simple integration. So in this case, we can actually have the analytical solution. In this case, integration of the 1 of n. This function has the value of 1. Now, I'd like to take the uniform samples. And basically, at first sample, we got the first sample got the 0.86 summary here. Then our estimator. This is the Monte Carlo estimator. Basically, when I mentioned Monte Carlo estimator, it's nothing but the secondary estimator, and then it has a value of the 2.74, which is very away from the 1. And next sample, we got this value here, and then now it gets bigger. It gets smaller, 1.44 and 4. And this third sample, you got the very small value. 0.02, and then our estimator now becomes some value smaller than 1. And now we got this value, and then again now we got this small value, even smaller than this 0.96. But as we take the more sample, it will actually convert to the 1. Now we'll talk about the 2D cases. Now the function fx actually has these two parameters, x and y. But our Monte Carlo integration just naturally can be naturally extended to the higher dimension. We just same thing, 1 of n summation of the f divided by p. Obviously, function f and p actually has these two different parameters since it's a 2D domain. Simply speaking, Monte Carlo integration works well for higher dimensions, unlike the quadrature. Basically, it's nothing but we just even though it has a 2D, we just take the random sample for the xi and yi, and then that's it, just point sample. Even though we had this 7-dimension or 10-dimension, we just take this point sample in that high dimension. That's why actually the Monte Carlo integration very general for handling the high dimensional space. Actually, the random equation also can have the very high dimension, 7 dimensions, even 10 dimensions. So that's why we are using this Monte Carlo integration. Again, basically these are the advantages of Monte Carlo. The convergence rate of our Monte Carlo estimator. Basically, in this case, actually, I'm talking about this. I'm talking about the standard deviation, not variance. Standard deviation standard deviation has the shape of the big O of 1 divided by the root n. But variance, we can simply use the variance of Monte Carlo estimator has a reduction rate of the 1/n. It's a very simple concept, right? Just sampling. Also, the point evaluation. We just take we just generate a random sample, and then at that point random sample, we evaluate the function fx. Then that's it, right? We take the average, right? It's a very general concept. Works for high dimension. Also, it can deal with a very arbitrary function that has a discontinuity and very odd shapes. Let me record this random equation. Suppose that we want to compute the reflected radiance from the point x. Let me use the mouse pointer. This point x in the direction of this big theta. Then to compute that radiance, we need to put the hemisphere here at the center of this x, and then we need to consider incoming radiance in the incoming direction of the put side to the point x, and then we need to consider the BRDF adjusted by the cosine theta. Then if we consider all the incoming radiance, then we can compute this reflect radiance. Then here, to solve this reflected radiance, we need to consider this incoming radiance, right? So if we visualize this incoming radiance into the rectangular shape, basically we actually put the hemisphere, right? And then we just transform that hemisphere, the region into rectangular shape. This is actually incoming radiance. You can see that at that point, we can see the light source, and here actually we don't have light source, but we can see this surface, this material, since there could be the reflected radiance again here, right? So the random equation to solving to compute the reflect radiance, we need to consider this incoming radiance. Before I talked about the reflect radiance, but now I talk about the overall radiance from the x to that direction, outgoing direction theta. Then first, in terms of algorithm wise, we need to first check whether that the material x is actually the emitted. Does it emit something? So in other words, is it some sort of the light source? Then we need to consider the reflect radiance, right? By solving this random equation. So that random equation is complicated integration. So we can use the sampling approach, specifically this Monte Carlo approach. Then we generate random direction on the hemisphere using the big psi, using some sort of the PDF function. Let's say p of this psi. For the time being, you can just using some sort of the uniform sampling of the hemisphere. Then the reflect radiance shown the reflect radiance represented in the random equation. We can actually compute we can apply the Monte Carlo integration. Then this is our Monte Carlo estimator. So we take the n different samples and we sum them up. This one divided by this p of the psi I, and then since there could be there are n different random number, we need to take the 1 of n. Then this is our this unbiased Monte Carlo estimator. Then the question is that here n is known, this is already given. We define this uniform sampling for this p of psi I, and we know this BRDF at that position. Also, we know the cosine theta value. But one thing unknown term is this incoming radiance. Basically, to compute the outgoing radiance, we need to know we need to again compute the incoming radiance to the point x in the direction of psi I. The question is how can you compute this one? As you can see, there are recursive structure again, right? And this one actually, this x, and then we need to compute the radiance value from here. in the direction of psi I value to I, right? But we just assume this reciprocity of this radiance value. So we can just the radiance value from here to there is same to the radiance value from here to there. So that we can simply using the ray tracing in a backward way. So we just compute the ray tracing from the direction x to there. So then basically to compute this outgoing radius, we need to compute we need to perform this ray tracing in a we need to perform this process in a recursive way. So also as you can see, each additional bounds supports one more indirect illumination, right? So by considering the backward direction, we can consider one bounce from here. We having the one interaction from the light source and material, and then we need to compute the reflect radiance. So as we have this more bounds, we can actually consider more indirect illumination, and then we can compute the additional bounds, and then basically we can get a better result for the global illumination. Then the question is that when we have to terminate this recursive process, and basically this is actually visualization of as we have the more bounds. As you can see, this initial bounds. So at the initial bounds, actually there's a light source. We can see that. Otherwise, we don't see any light value since we just here. But as we have the more bounds, we can get the more additional. We gather additional light source. As you can see, we can get a more better and better result considering this global illumination. Then you can observe that as we have the when we consider only the one bounce, second bounce, you can get a lot of the additional light energy. But as we had more bounce, the delta from by having the additional bounce is actually becomes small. So contributions of further light source further bounce become less significant, right? So that actually we can consider some sort of max recursion. Say we can just consider only 10 recursion, right? And then we only allow the up to 10 recursion, right? We can do that. But actually, if we just ignore at the point once we reach the max recursion and then we just terminate it, then it means we just simply ignore all the additional light energy that comes from the additional bounce more than 10, right? Then estimator will be biased. So basically, Monte Carlo approach is unbiased, right? But if we adopt this kind of the deterministic approach, it will be it cannot be the random process. It is actually, it has some sort of the deterministic approach. It introduces some sort of the bias. So we need to rely upon some sampling approach. To terminate this infinite recursive process, we typically use this Russian roulette. So suppose that we wanted to compute this integration. So we need to integrate in the range of 0 to 1 of for the function f of x. You can basically we can visualize this function as shown here. This is 0 to 1, and then the function f of x is this black curve. And then to solve this process, we can also use this simple trick. We substitute y. Basically, we define the y as y to be equal to the p of x. P and multiply x, and p is the some number in between 0 to 1. So you can see that p is 1. And then our idea is that we wanted to make the final function to be 0 in the range greater than p. So at that case, we don't get any value. So that actually, in other words, it can technically terminate this recursive process. Since we cancel the value to be 0 here, right after p, we need to compensate that value, right? So that actually for other range that less than p, we need to actually make this function bigger than the original function. So basically, you can see that we can somehow actually transform this function into this blue function like this. So in other words, we actually substitute y to be the p multiplied x, and then this function actually reformulate like this. We integrate the 0 to p, and then we got in the range of this y value, and then we get this function. And then basically our this is our Roshan ruler estimator. Then if this x when you generate random number xi is bigger than p, then we got the zero value. But the random number is less than p, then we got this value. So f of xi divided by the p actually. Yeah. So basically this is our final integration. Then and then one can show that the Russian roulette estimator is unbiased. I'm not going to talk about the detail here, but I think that my book already showed that this unbiased. So if you're interested, you can look up you can refer to my book. And then intuitively, we can say that this variance of the variance of Russian roulette is bigger than the original one, right? Why? At the case we got the zero, but in this region we got much bigger value, right? So the value actually change more, so the variance becomes more the higher. But even though each variance are higher than the prior one, we can at the case once the random number turn out to be bigger than p, we can terminate the recursion process. So actually, this is we can adopt this process. So and then the 1 of p is the absorption rate, absorption probability alpha, and then as an amount of alpha, this recursion is terminated. And then the p-value is basically p-value is set to be equal to the reflectance of the material of the surface, right? Basically, in the range of p, we actually somehow reflect the energy, right? So that once we know the reflectance value of the material, we can define the p-value, and then accordingly we can also compute this alpha value. So in summary, so in the past, we were actually talking about the past ray tracing. We actually generate multiple primer rays through each pixel, and then once the primer hit at some material, then we also generate the indirect rays or sample over the hemisphere, right? And then we keep doing this recursive process, but we terminate this recursion process by using the Russian roulette. This algorithm, so far it's not a path ray tracing, but actually path ray tracing actually has a very minor change into this algorithm. So basically, this Monte Carlo ray tracing, which seems very simple. And basically, we can compute the radiance value only at the center pixel. But if we do that, actually, this will generate aliasing, also known as this jaggies. So basically, we typically to address this aliasing, we generate multiple rays even at each pixel, right? So then we can just, in other words, we can just use the Monte Carlo approach. We can generate n different samples within this pixel, and then once we compute the radiance value for each ray, then we compute we evaluate the Monte Carlo approach, and then we just take the average, which is known as the simple box filter. I can talk about I can talk about a lot of things why this averaging method is a box filter, but this basically I'm not going to talk about the details here, but basically this is the averaging method actually turn out to be the box filter shape in the frequency domain. There could be many different parameters for this Monte Carlo ray tracing. One is this number of starting ray per pixel. Basically, this our eye. Let's say this pixel, and then we can actually through this pixel we can send one ray, but also we can generate additional ray, right? But basically how many this external ray we generate. Once we compute radiance here, this primary ray, also we compute the radiance here, we can just averaging them out, right? Another one is we can also once this given this primary rate, in some cases actually this might be intersected with some object, and then we might need to generate this additional secondary ray over the hemisphere, right? And then that's for each surface points we can generate the different number of the secondary ray, right? That's also this could be the different number of random ray, a different number of this indirect ray, but that's actually we call it also this branching factor. But here, this path tracing actually which only generated one this indirect ray. So suppose that again in summary, given this our eye, for pixel we generate this once we generate the primary ray, and then if it is intersected with a certain object, and then given this intersection point, we actually generate one additional the secondary ray, and then also once it is also intersected with another object, and then for here also along the hemisphere we also generate another another secondary ray, and once it hit it with some sort of light, and then we can actually compute this energy, and then we can transfer that energy from here to there, to that our eye. And then if you see that actually there are one path, right? This actually light path. So that's why once we had the branch factor 1, we call it path tracing. This seems to be I cannot talk about I mean there are lots of details, but I'd like to skip the details. But in the end, this simple idea, just using one branching factor that generating the light path, turn out to be one of the simple but actually very powerful Monte Carlo ray tracing technique. And then a lot of cases actually there are so many advanced technique than this one, than this path tracing. But whenever you generated new algorithm, a lot of cases you need to compare the new algorithm against the path tracing algorithm, which is kind of this ground truth or the reference algorithm. So this is the result when we use the path tracing. This is the result, the rendering result when we use one sample per pixel. So in each pixel we just use one sample. So then in other words, we generate one primary ray in each pixel, and then we compute we compute the one path, right? So as you can see, since there are only one path in each pixel, you can see that it has a lot of noise. But when we are using the four samples per pixel, it gets better. And then we generate 16 SPP, we got a much better result. In this case, we use the regular pixel sampling. Also, we additionally use the light source sampling by considering this importance sampling, which I didn't talk about yet, but I will talk about this issue later on. But anyway, by using these two different sampling techniques, pixel sampling and light source sampling, you can get this kind of result. So in summary, we generate the primary rays through each pixel. Also, we shoot indirect rays over the hemisphere, but path ray tracing shoot only one indirect ray. And then we keep doing that, and then we generate paths, but we terminate this recursion process using the Russian roulette. Okay, so that's it. So by now, I hope that you can understand the high-level structure of the Monte Carlo ray tracing. So we talked about the Monte Carlo integration, general numerical integration, general numerical solution for computing evaluating very complex equation like the random equation. And then we apply this Monte Carlo integration to design the Monte Carlo ray tracing. And also due to the recursive structure of ray tracing, actually we cannot terminate, but basically we introduced the Russian roulette for terminating this recursive structure of ray tracing without generating bias, which is actually without generating this kinds of the systematic error. And then we also given this primary ray, we only generate one indirect ray, which is actually branching factor 1, and then we call it that algorithm as a path tracing, which is actually one of the reference algorithm. And then actually we actually skip this rigorous analysis to actually derive the bias variance of any kind of this numerical solution, which is very important for this physically based algorithm, since actually in the end we are using this Monte Carlo approach to not to generate any additional arbitrary error, but actually we skip this one. Also I didn't really talk about this importance sampling, since actually if I talk about it, it requires too much actually theoretical analysis. So actually I decided not to skip that kind of complicated approach. But I hope that you can understand high level structure. And then in summary, in this class so far I talked about early on I talked about rasterization based rendering, which is actually that's why we talked about rendering algorithm. Also we talked about the various transformation, including the camera transformation and so on. Also, we talked about calling and clipping, illumination, rasterization, also the texture mapping. Actually, in the case of the rasterization, if you wanted to generate additional effects, so for like the shadow mapping, we need to actually think about it. We need to utilizing some sort of this additional texture mapping to enable that kind of effect within this rasterization scheme. Overall rasterization technique actually it is actually kind of the create algorithm for achieving the very fast rendering performance, but actually this is not physically based. So that's why I briefly move on to the physically based rendering algorithm through this ray tracing algorithm. Also, I talked about the basic radiometric quantity like the radians, and then also talked about BRDF. And based on that, I talked about the rendering equation. I talked about the Monte Carlo integration to solve this rendering equation. Okay, so and then there are many other other related courses in here at KAIST. Actually, there are also this graduate level of this advanced computer graphics CS580. And then basically it focuses more on the rendering technique, more advanced technique that generate the photorealistic rendering. Also, there are another kinds of advanced undergraduate level computer graphics, CS482, which also talk about the more this advanced technique on the rendering. Also, talk about some of the recent deep learning method. Actually, I will teach this CS482 in this fourth semester. So if you're interested, you can actually you can think about take this one. But this is actually more this course in this course actually this will be more the research oriented course. So in addition to the presenting papers, also you need to actually carry on some of the research oriented this project. Okay, also the incoming lectures, also I also prepared some of the talks on some of the recent deep learning method, including the denoising techniques, also the nerf-based technique, also the diffusion-based also the generation technique. So I'd like to give you the opportunity to hear about some of recent technique. Okay, that's it. See you in incoming lectures.